Good morning, everyone. I got an email from one of you last night, and so I want to start with an announcement, a sad announcement. Yeah, the LA Times. So Dan sent me this saying Paul the octopus died earlier this week from natural causes. You do? You suspect malplay? Anyway, so there he is in his glory, but he won't be around for the next World Cup. Okay, so today we're going to do two things. We're going to wrap up hypothesis testing, and we're going to revisit the central limit theorem with a problem that I hope you'll find related to your lives. From what I've seen is that many of you, when you turn 21, take a trip to Nevada. And so this will just be a little life lesson for you. All right, so first hypothesis test. So we're going to look at averages, and here's an example which I was being incredibly frivolous, and so this is not at all based in reality, aside from the fact that this cereal really did exist at one point in time. So we're now dealing with a box. So on the top, we have quantitative data, not qualitative data. So we don't have a 0-1 box. We have a box. We're going to have a box with numbers other than just zeros and ones, and a known standard. So the problem is this. That's Cecil, the cantankerous machine over there, who's supposedly very, very grumpy. And then there are 4 people named Grins, Smiles, Giggles, and Laughs. Believe it or not, this was actually advertised in the 1970s. There are 2 of those characters there who sort of tickle the machine, get him into good humor, and make him laugh. And when he laughs, he shoots out cereal boxes from his mouth. Needless to say, this cereal is no longer on the market, but it was introduced in 1976, and there are some people I've found on the web who still say it's their favorite cereal. I think it depends on how old you are when these things are introduced, right? So some of us love Captain Crunch because that was the new cereal. Anyway, so suppose that the cereal box, if you read the lower left corner there, it says it's 8 ounces of cereal. And suppose the cereal box, therefore, claims there are 8 ounces of cereal in it, and you buy a box every week for 25 weeks, and you weigh it before you eat any of it. So if you love the cereal so much that you want to be sure that you get 8 ounces each week. So here's the data. The first week, there were 8.29 ounces of cereal in the box. The next week, 7.68, 7.67, 7.62, ... all the way up to 8.28 in the last week. So you would like to test the hypothesis that that the company actually does put 8 ounces of cereal in the box. So in that case, you can think again of a possible box model where when the company's filling up, the manufacturer is filling up the boxes with cereal, they shoot for 8 ounces and there's a little bit of an error involved. Unfortunately, you don't know the error, and we would assume that the actual measurements of these boxes of cereal is 8 for the 8 ounces plus the error. So our test statistic would be the average weight of the 25 boxes, which in this case, when I take the average, I get 7.9. My expected is this known standard. It's what's advertised on the box, which is 8 ounces. So the question is, my null hypothesis would say, really, there are 8 ounces of cereal in the box on average, and any observed deviation that we see is due to just the kind of random fluctuations with a sample of 25 from all the boxes of cereal that that they're producing. So the standard deviation, or the standard error for the average, we saw on Monday, was just the SD of the box divided by the square root of the sample size. So the SD of the box, unfortunately, is not known. We know the square root of the sample size. Square root of 25 is 5. But we don't know the SD of the box. So when we look at how far away is 8, what we expect, from 7.9, what we observed, that's 0.1. But that could be really large depending on the standard error for the average, or it could be really small. So we really need to know how far away is it in standard units to be able to make any kind of conclusion. So I could plot the distribution of the tickets in the box. Excuse me. We don't know the distribution of the tickets in the box. So I could plot the density plot for the distribution of weights that I've observed in my sample, and that's what I've plotted right here. Notice that you would kind of think that the sample would look something like the distribution of tickets in the box. So does it look normal? No. Does it look, well, it looks kind of bimodal with a value around, one mode around 7.6 and the other mode around 8.2. So the sample doesn't look normal. But what do we know about what does the central limit theorem, before I go there, what does the central limit theorem tell us about the average of a large number of draws from a box?
The average will turn out to be normally distributed?
The probability distribution for the average will be normally distributed. So we had that little exercise at the end of class on Monday where you were going to make up some sort of box to see if you could beat the central limit theorem. And we showed, hopefully you were somewhat convinced, that the central limit theorem takes over no matter what the box looks like. Although, depending on what the box looks like, it might take longer for the central limit theorem to take over. So the central limit theorem says that if we sample a large number of times from the box and take the average, that the probability distribution for that average, so what are all the possible values that you might get for the average and the chance of getting those particular values, that should follow the normal distribution. So we can, if we think about it that way, we can then say, well, let's just use then the normal distribution as an approximate distribution for the sample average. And at the same time, we can also approximate the standard error by plugging in the SD for the sample. So we're making two kinds of approximation here. One is to say, we don't know what's in the box. We're taking an average of tickets being drawn from that box. So we're going to say, if our number of tickets being drawn from that box is large enough, it seems a pretty safe assumption to think that the probability distribution, the null model for our sample average, should be close to normal. So the sampling distribution of our test statistic, which in other words is saying what's the null distribution for our test statistic, follows an approximate normal curve. And we observed the 7.91 minus 8 divided by 0.056, which is the 0.056 is an approximation for the standard error for the sample average. So it's the SD of the sample divided by the square root of 25, where really the true one is the SD of the box, which is unknown. Okay, so we get a minus 1.639. We say, well, how large is this statistic? Now we can use the normal to compute it. So we can use the p-norm to say, so should this be one-sided or two-sided? Is this a one-sided or two-sided test?
Two, because you're going to have either a lot less than 8 ounces or a lot more.
You could have a lot more than 8 ounces, but are you going to complain to the company if you get a lot more? Probably not, right? You really care about whether or not you're being cheated of your 8 ounces of cereal. So in this case, the alternative hypothesis is that the company puts less than 8 ounces of cereal in the box, and so it should be a one-sided test, not a two-sided test. So we can then look at, yes?
Does the one-sided test apply to all of the hypothesis averages, or
Just this particular situation where we only care about if we're getting two too little cereal. Other questions? So an example of one-sided but on the other extreme was that coliform, when you're testing your water sample and you're concerned if you had too much pollutants in the water. And so 250 was the cutoff, the EPA recommended cutoff, which I made up. But we cared again about something one-sided, but was my observation my observed value, is it above the 250? So far above that I couldn't attribute it just to chance variation. Here, we're also one-sided, but we're on the other side, saying, do I have too few ounces on average? But there could also be a two-sided one as well, depending on the problem. So it's one-sided. So the p-norm gives me the tail I want. It's the lower tail, and it's 0.0506. So technically, this is one of these funny things where you got something that's really close to 5%, but it's over 5%. It's higher than 5%. Therefore, you do not reject your null hypothesis that the company's putting 8 ounces of cereal in the box. But you might still be somewhat suspicious and wind up wanting to collect more boxes of cereal and continue your measurements because you're just on that borderline of the 0.05. Any questions about that? So this kind of test is called the z-test. And that's because z is connected with the normal distribution. And just as a quick summary, if we've got a non-zero one box, so we've got all different kinds of tickets in our box, and we don't know what the distribution of tickets in the box looks like, but we are taking a large number of draws from that box, large enough so that we think the central limit theorem will take over for the probability distribution, then we can use the normal curve as our null distribution. And in which case, the z-test, which essentially is computing tail probabilities for a normal curve, can be used. All right? There's one more distribution that I'd like to introduce you to for testing, and that's the t-distribution. The t-distribution comes into play with some very special case, and that's when, again, you don't see the tickets in the box, but for one reason or another, you know that the tickets in the box have a normal distribution. And the box SD is unknown. So you know the distribution of the tickets, but you don't know the actual SD of the box. So you know it's normal, but you don't know the SD. So if the number of tickets drawn is small, you can still approximate the SD of the box using the SD of the sample. And when you do that, that kind of error that gets introduced in that approximation means that the test statistic, where we take the sample average, subtract the known standard, divide by the estimate of the standard error for the average, no longer follows the normal distribution, but it now follows the t-distribution, and that's when we use the t-test. So what is the t-distribution? The t-density, there's a whole family of them. They're all unimodal, symmetric around 0, and they are distinguished by their degrees of freedom. The degrees of freedom basically tell you how fat the tails are. So a low degree of freedom have really fat tails, and as the degrees of freedom increase, the tails get shorter and the peak gets higher and it gets more and more normal looking. Basically, these degrees of freedom are telling you how much information is going into your approximation for your standard deviation for your box. So if you've got a large sample size, then you've got a very good estimate for the SD of the box. So your degrees of freedom are large. In fact, it's n-1, where n is the number of draws. And the t looks quite a lot like the normal. So here's a picture where I've got 3 t curves, or three t densities, and the normal. So the normal is a green one. A T2, 2 degrees of freedom, is the blue. So you can see its tails are the largest of all of them, and the peak is lowest. And that's sort of saying, well, because I don't know my SD of my box, I'm having a pretty lousy estimate of it, and so I could get some really wild, I need to increase basically the variability. The T8 is the orange, the T20 is black, and you see by the time we're up to 20, it looks really quite close to the normal. So if you know your box is normal, by the time you've drawn about 20 tickets from the box and taken the average, you get a pretty good estimate for the SD of the box using the SD of the sample. And so the T with 20 degrees of freedom means you've actually had 21 draws from the box because you subtract one. But you would do a pretty good job just using the normal.
That left label, is that T norm X or?
Excuse me?
Is that the left label, should it be D norm X or?
Oh, I didn't control my labels. It should just be density. Yeah. So the first one I plotted was the normal. And yes, that should be density, the axis label on the y-axis. So just to give you an idea, if we go back to our serial example and take the SD of the sample and plug it in for the SD of the box, because we had 25 observations, we have 24 degrees of freedom in estimating that SD. And if I use the t-curve of minus 1.639 with 24 degrees of freedom, I get 0.057 as my p-value in comparison to 0.051. So they are really close at this point in terms of the difference between what's going on in the tails. Okay? So that shows how the tails are actually fatter. Any questions? I just want to tell you about a little function in R that does these calculations for you for the t. There's a t.test that performs t-tests for you. And essentially, you give it your data, which is the weights. You give it your standard, which is the mu parameter. So in this case, mu is 8. And you tell it whether you want a one-sided or a two-sided test. If you want one-sided, you tell it whether you want the left tail or the right tail. In this case, I say less, and less means I want the left tail. In other words, my alternative is that mu is less than or equal to 8, or less than 8, I should say. And then this is what comes out of it. We get out the mean of the data, the 7.9, and we get out the p-value, 0.057, and the degrees of freedom, and the actual normalized test statistic of the 7.9 minus the 8 divided by the standard error, or the estimate of the standard error for the sample. And there are other ways you can use the t-test, which we will see later on in the semester, but this is the very basic when we have a known standard. So what I'm going to do now is I'm going to summarize this is the way to think about how to determine what kind of test you should be using. So I think that the two most important questions are to think about your data. So we go all the way back to those first questions of what kind of data do I have? Do I have quantitative data or qualitative data? If I have qualitative data, that's sort of nominal type data. I'm therefore looking at counts. If I have quantitative data, those are like the weights of the boxes of cereal. And the other question to answer is, what am I testing? Do I have a known standard that I'm comparing against, like the 8 ounces of cereal? Or am I comparing two groups and wanting to know if they're different? And I have data for each of these two groups. So those are the two crucial questions, and then there are more questions to answer for some tests versus others, but that's the start. So I'm going to go through each of the 4 combinations. Qualitative, a known standard; qualitative, compare two groups; quantitative, a known standard; and quantitative, compare two groups, and show you the different tests that you've seen so far in the semester. So first of all, qualitative and a known standard. An example was the roulette wheel landing red, and the question was it fair or not? So then there's a known standard for that. If it's fair, we know that the chance it lands red should be 18 out of 38. Another one was the number of men in the sample that Albert took, where he found he wound up with, I think it was 47 men, but we knew that at Berkeley, the percentage of men in the population was 60-something%. That was our known standard, and we're comparing what we got in our sample to the known standard. Because it's qualitative, we're using the 0-1 box. Our test statistic will be a count, and our null distribution will depend on whether we're making draws with or without replacement. With replacement, it's the binomial with the number of draws and the proportion of ones as our two pieces of information. And it's hypergeometric if we draw without replacement. Okay, and when we have a box with lots and lots of tickets and we don't replace, as long as our sample size is small compared to the size of the box, we can plug in the binomial or substitute the binomial for the hypergeometric. So that's one of the four. The other one is, the next one is qualitative, and you're comparing two groups. An example is the Salk trials. We were looking at the incidence of polio. Did you get polio or not? So that was qualitative data. But we were comparing two groups. We were comparing those treated with the Salk vaccine and those who were not treated. In this case, we again have a 0-1 box, but what we do is we put tickets, all the tickets in the box, one for every person in the trial. And a 1 will be for the quality appearing, which in this case is polio was contracted, and a 0 for those who were healthy. So we take all of the data from both the treatment and the control, put it in the box, and then we basically simulate the experiment, assuming that the assumption, the null hypothesis, is that nothing's going on, the vaccine doesn't work. We make draws from the box, and we will draw out one for every person that gets assigned to treatment. And so we're drawing without replacement, and we count up the number of ones, the number of polio cases in the treatment. And so that null distribution is a hypergeometric, where we have the number of ones in the box, the number of zeros in the box, and the number of draws that we make from the box. Where in the Salk trials, the ones stand for the polio cases, the zeros the healthy cases, and the number of draws is how many are in the treatment group. Questions on that? So those are two that you've seen so far, the two for qualitative data. Now, for quantitative data, there's quantitative data in a known standard. The two examples that we've used in class so far is the one we just talked about with the weight of the cereal box, and the known standard is 8 ounces. That's what's advertised on the box. The other is the coliform levels in the water samples, whether or not it exceeds 250 or not. So in those cases, we don't really know what's in the box, aside from knowing that there are numbers on the tickets. They're not 0-1, but we don't know exactly what they are. But we do have the average for the box, and that comes from the known standard. For the cereal, it's 8, and for the water samples, it's 250. So then the question is, well, do you know the SD of the box or not? Do you know whether the tickets look normal or not? And depending on that, you might do different tests. But the important thing is that we look at the sample average, we subtract the known standard, and we normalize it to see how big that difference is by the standard error for the average, which is the SD for the box divided by the square root of the sample size. Then what the null distribution is going to depend on whether the tickets are normal in the box or not, whether we have a really large, that's right here, whether we have a large sample size or not. And here are the possibilities that we've studied so far. Okay, what's the null distribution? Or is the null distribution normal? So we do the z-test. If the sample size is really large, then the central limit theorem says, hey, it's okay to use the normal. If the sample size is small, but you know the box is normal, and you know the SD, then it's okay to use the normal. If the sample size is small, but you know the box is normal, but the SD of the box is unknown, then you can use the t with n-1 degrees of freedom. And you might say, well, that doesn't cover all the cases. And it's true, it doesn't. What about a normal, a non-normal box with a small sample size, and we're not going to cover that. So these are the sort of 3 situations that we'll cover. Okay? All right. The last one is quantitative when we compare 2 groups. So we have seen one example of this so far. That's when we're looking at the blood pressure in 2 groups of men, one that was given calcium supplements and the other that was given a placebo. And we looked at the difference in their blood pressure taken before and their blood pressure taken after 12 weeks of treatment. So each one has a number which depends on whether it's really big, I can't remember which way the difference was taken, whether big is good or big is bad. But depending on which number you subtract from which, suppose we start with the initial and subtract the final. You'd like that to be a big number to say the blood pressure is really decreased. So in this case, what we did was we put all the measurements from both groups into the box. And then we drew out, so very much like the Salk trials, we drew out the number that belonged to the treatment group. And we computed the average. And then we repeated that many times over. We didn't get an exact null distribution for this. We used sampling techniques in R to figure out the probability that the observed average would be as large as it is based on the box. So saying, again, just like with the Salk trials, saying that it's just by chance that these people wound up in the treatment group, that the treatment really has no effect. So I'm just going to sample over and over and see how likely it is to get the average that I did get. And that's called a random, I didn't give you the actual name for it, but it's a randomization test. Okay. Last thing, 3 lessons we have basically skirted around about hypothesis testing. And I want to make sure everybody's aware of them. The first one is the difference between practical significance and statistical significance. So statisticians have hijacked a lot of everyday words and used them in a very precise way. And so significance is one of them. So we put the adjective statistical in front of significance to let you know that what's behind it is an actual hypothesis test. And the point that we're making here is that that could be very different from something being practically significant. And what I mean by that is, yes, you might reject your null hypothesis saying that there's no difference between these 2 groups. But then the question is, well, how big was that difference, and does it really matter, practically speaking? And although we can detect very tiny differences between 2 groups, if we have large samples and do our hypothesis test, it might be that those tiny differences are really not important. And that's what we mean by practical significance. So in reality, when we're doing a lot of these hypothesis tests, we don't really believe that something is exactly 8 ounces, or we don't really believe that 2 groups are really exactly the same. And if we uncover that, in fact, that they are different, then the question is, well, how big is that difference from a practical standpoint? And statistics is, in this case, the hypothesis test, is not helping us make that decision. Okay, the next one is 5% of the time, you will, in fact, if you're deciding to reject a null hypothesis based on the p-value being less than 0.05 or not, 5% of the time, you will be rejecting a null hypothesis that is in fact true. I said that incorrectly. If in fact the null hypothesis is true and you're testing it, there really is a chance that you will reject it, and that's the p-value, or that's the 5%. Does that make sense? So remember how we compute the p-value. We're saying, well, suppose this really is true. What's the chance I observe something as rare as what I observed or not? And you're willing to say, If I've observed something that's really rare, i.e. that happens only 5% of the time, I'm willing to reject my hypothesis, that whatever my hypothesis is. So you are actually saying that although it's possible to produce a result like this one, it is so rare that I no longer believe my hypothesis is true. Yes?
But wouldn't that mean that, like, out of 20 null hypotheses, like, one of them...
Very good. That's a very good observation. That means that out of 20, if you have, in fact, I was looking for a study and I couldn't find it. But what Manish is saying is that doesn't that mean that if I do 20 hypothesis tests and every time the null hypothesis is really true, I'd expect to be rejecting one of them? And yes, that's true. So if you don't like that risk, then you change it to 0.01. And that means out of 100, you expect to be losing one, rejecting one, when in fact it shouldn't be rejected. And if you don't like that, then you take an even smaller one. So determining what the cutoff level is really important. So if you really don't think it's a good idea to be rejecting a null hypothesis that you might be rejecting 1 in 20 times just by chance, then you don't pick that as your cutoff level. Lots of times people, in fact, simply report the p-value and leave it up to the person who's looking at their study to decide what to do with it. So, for example, I heard on the news more than a year ago about someone who did a study, large study, where they measured things like what's your favorite color, what's your astrological sign, do you get out of bed on the left or the right side. They had like hundreds of these variables, which were clearly all meaningless. And they looked at correlations between these variables and things and health variables. And they computed all sorts of hypothesis tests as to whether or not there was a correlation between your sign and your predisposition for cancer or something like that. And in fact, they found some highly statistically significant results. So their hypothesis in each case was that there is no relationship between these two variables, but they did so many tests that they did in fact find that if something like if you like green or your sign was, Sagittarius or something like that, that in fact there was a connection between that and some health issue. And so here's Paul, the octopus. And I thought I'd bring him back in honor of his passing. And and remember when we looked at that one, we found out that there were at least 20 other zoo animals around the world who were trying to predict the World Cup as well. And so that's exactly what could happen, is that if none of them actually have any predictive capability, but we're testing 20 different ones, it's possible that one of them could wind up being successful. Last lesson learned is there's only so much you can draw from a rejection of a hypothesis test if it's based on a poorly designed experiment or if it's based on an observational study, which is not a designed experiment. Because you have to look into all the reasons why things might have gone wrong. And when you have a very well-designed experiment where you've controlled lots of factors and the only thing really differing between, let's say, two groups is the treatment, then you're happy to conclude when you reject the hypothesis that the treatment works. But if you have a poorly designed experiment, then there could be other factors that make the two groups different, which then lead to the rejection of your hypothesis. So it's really important to have highly well-designed experiments. Similarly, with observational studies, which we'll be getting into next week, but with an observational study, since you're not controlling who gets whatever characteristic or not, that when you observe significant differences between groups, it's hard to know whether that's due to the particular characteristic that you're looking at or some other potential confounding factor. All right, that's it for hypothesis tests for now. They will be resurfacing as we go through the rest of this semester with some of our linear models and that sort of thing, but that's it for now. I want to segue into this, what I advertised at the beginning of the lecture, this, the central limit theorem coming back for us to discuss. And I also want to say that on Friday, this survey will be due, which is the survey that's going to help me figure out what teams that you'll be assigned to. So it will be posted on BSpace very shortly with instructions, but so keep your eye out for it. All right, so here we go. Here's a roulette wheel. I'm going to put it up here on my document camera. Hopefully that will work. Okay. So does anybody know, in fact, how these roulette wheels work? You know, it's very, yes, you know?
Spin it one way and throw the ball around.
That's right. You spin it one way and you throw the ball in the opposite direction. Now, I don't know if my roulette wheel is well balanced or not. You know, it's kind of, and it is settling on red 9. So if you had bet red, if you'd bet $1 on red at this point, they would be putting an additional $1 down for you, and you keep your $1 and you get one more $1. If you'd bet number 9, do you know what you get? 35. 38 would make it fair, but you get 35, I believe. And so it works like this, right? So wait a minute, I spun it this way, whoops, and so I do it that way. So let's say we bet red, and we'll see if red comes up or not. So you have to place a bet, like $1 bet. If it comes up red, you win $1. If it comes up black or green, they take your $1 away. Oh, we won again. What do you know? So does that mean we should be heading to Las Vegas? What's that?
Shenanigans in the roulette wheel.
Okay. So I want to ask you, what's the chance that I win when I place $1 bet on red? You know this. We beat this example to death the other day. What's the chance that you win? 18 out of 38, right? There's 20 and 18. There's 18 blacks, 18 reds, and 2 greens. If I'm interested in my expected winnings, so not whether I win or not, but my expected winnings, so how much money am I going to win? How does that change the box? So I'd like you to tell me, what box should I use if what I'm interested in is my winnings? Yes, in the back. Okay, I like the start of that. You said you get $1 if you win, so you want a +1. 18 of them. Okay, and what else? You lose $1 if it lands. Good. So it's -1 for how many tickets? 20. Sharada.
Wouldn't it actually be like -1 for 20 tickets, 17 plus 1, and then 1 ticket, then 35?
Oh, you've never played roulette. You can bet red, or you can bet on a number. So or maybe you have played roulette. Here, wait a minute. An important piece of the puzzle is the roulette table. Here it is. So you can either bet on a particular number, or you can bet on a color, or you can bet 1 to 12, 13 to 24. You can bet on a group of numbers. You can bet on a row of numbers. And we're just doing so let's see if we can put that there. We're just doing the simple bet of red. We're not betting on a specific number like 21, nor are we betting on any group of numbers, nor a row of numbers, none of that. So if you bet on 17, oh, I wanted to show you, I did some little web research on number 17 after Monday's class. I'll have to show it to you later. But if you bet on number 17, then if it turns, and the color of this says that 17 is a black thing. If a black shows up, but it's number 20, for example, you don't win, you lose. So let me ask you this. What does the box look like if you're betting on number 17? There's only one possible win, and so there'll be one ticket with a positive value on it, and then there will be 37 tickets, because there are 37 ways to lose, all with -1. So there'll be one ticket where you win $35, and then there will be 37 tickets where you lose $1. Okay. Okay, so that's what our box looks like if we're just betting on red for $1. So, and we take a draw with replacement. So what's the expected winnings? Can anybody do the math there really quickly? The average of the box? Right, thank you. It's the box average, which would be adding up 18 ones and adding up 20 negative ones, and that is -2 over 38, which is very close to 5 cents. It's I think it's 5.6. So what does that say? This is one of the first lessons. Is it says that you can expect to lose a nickel for every dollar you bet on the roulette wheel when you're betting red. Okay, remember that? You can expect to lose a nickel for every dollar you bet on red when you play roulette. Okay, so let's say you just decide that you're going to spend a month in Las Vegas. And you're going to bet every time on red on that roulette wheel, time after time after time. And you're going to just bet for as long as you possibly can. They bring you drinks, right? So you can stay there for a while. Suppose you're able to manage to place a bet. Suppose you can bet on 25 spins of the roulette wheel per hour. And you're so psyched that you only need 4 hours of sleep a night. And so you're going to bet for 20 hours a day. And there are 30 days in the month. And that comes to, yes, 15,000 spins of that roulette wheel. How much money do you expect to win on 15,000? Yes? Betting, yeah, it's really simplistic. Like you'd think maybe you'd get a little more sophisticated after a while, but you're just betting $1 on red every time. So you better bring all of your college savings or your tuition money, because what you expect, we know, is the expected sum is just the number of draws from the box times the box average. And it's that little nickel that you're expecting to lose every time that starts to add up. And it's a minus $789 is what you expect. You say, well, that's what you expect, but maybe you could actually really make some money also. So how do you figure out, well, what's the chance that you actually make some money? What's the chance you actually come out ahead? Yes? We could. So coming out ahead tells you what should be your value. Let's go with 0. Yes. And so how far away is 0 from minus 789? Well, you might want to say, I need a probability distribution to figure that out, right? So I might ask for, well, what's the probability distribution? And so what's the chance that I come out ahead in this game? Well, that's the probability that, yes? Oh, so let's say ahead. It's actually greater than 0, right? So what's the probability that my winnings are greater than 0? How am I going to compute this? I know what I expect is minus $789. But how am I going to compute this? Well, now that we have R, we could actually do it bunches of times, right? We could actually create that box with 20 negative ones and 18 plus ones, and take 15,000 draws from that box and add it up, and then do it over, and do it over, and do it over, and do it a million times, and then figure out how many times of those million is it positive. What's another way? So, Warren, I heard you earlier today explaining to Sophie something. The central limit theorem. How does the central limit theorem relate to this?
So what we can do is we can take lots and lots of samples from the box.
We have 15,000. So what does the central limit theorem tell us? The distribution of the sum of the draws, which are your winnings, should be roughly normal. So according to the CLT, the distribution of winnings is approximately normal. Well, very close to normal. And remember, there are two things we need to specify: the center and the spread. What's the center of this distribution? Yes? That's right. The center is what we expect, which is negative 789. And what's the spread? Do you remember how we do that? Were you going to tell me? No? Yes? Square root of the number of spins times. So it's the square root of 15,000 times what? SD of the box that's the spread. So box SD. The box, remember, has plus ones and minus ones, nearly 50-50, so the spread in this case is just about 1. And so this spread reduces to, when you do the math, it reduces to 119. So pretty close to 120. So now we can say, okay, here's my normal curve. It's centered at minus 789, and it's got a spread of about 120, 119. And where's 0? 0 is going to be way up here. And we can do the calculation. It's smaller than 1 in a billion. Okay? So let's back up and not take just your perspective of you spending a month betting 25 times an hour for 20 hours a day for 30 days on red. But let's look at it from the casino's perspective, where they have, how many roulette wheels are there in a typical size casino? Has anybody been in a casino recently? Do they know roughly how many roulette wheels there might be spinning? And how many people are betting on roulette. Yes? There's 5 or 6 roulette wheels in a casino in Reno. And there's probably more than one person betting on red for 25 times an hour. You don't have to do many calculations to find out how it is that casinos can make a lot of money. You can try it yourself. Suppose that there are 10 roulette wheels and there are 10 people betting, and all of a sudden you're multiplying that by 100. And so what their expected loss is the casino's expected gain. You take that 789 and multiply it by 100, and you're up to $78,000. Okay? So does anybody object to this? How many have like their grandma's favorite way of placing bets in roulette? So extra credit, if you have a particular system that somebody or relative has, if you can run a simulation in R to show what their expected gain is, if they are, so do something very similar to what I'm doing, what their expected gain really is. And you can't use slots, unfortunately, because slots, they're always adjusting the chances of winning, and so you never really know what's going on. But you can do a sort of probability R assignment due next Tuesday to, in fact, teach your relative or you or your roommate a lesson about the rules of gambling in Las Vegas. All right, so I'll see you all on Friday.